I want to say thank you to everyone for being here, especially Dr. Ahmad. This presentation is part of the series of outreach conference organized by the GESMAT group. Today, we have the opportunity to listen to Dr. Ahmad, and therefore, I allow myself to briefly read his path. Ahmad Mehdi is professor at the University of Montpellier. His research group belongs to the team Molecular Chemistry and Solid State Organization of the Institute Charles Gérard de Montpellier. He is co-author of more than 150 papers in the domain of organic and inorganic abril materials. Okay, now we are going to listen to the presentation entitled Inorganic Polymerization, Old Knowledge to Make New Materials. So, Monsieur Ahmad, vous avez la parole. Go ahead. Thank you.
Merci. Thank you very much, Sergio. Thank you for your kind presentation, and thank you for this invitation. For me, it's a great pleasure to talk about some recent results obtained last years in our team in a big laboratory, Institut Charles Gérard in Montpellier. It was a laboratory, its main focus on materials research, materials for energy, for health and environment. So it's very similar, like your axis in this way. And I would like to talk today about inorganic polymerization. I explain what this inorganic polymerization and how we can take this way, mineral polymerization, to prepare a lot of type of hybrid materials. I will focus my talk about biomaterials. This work, it's done with collaboration with my colleague in IBBM. IBBM, it's the Biomolecular Institute. So they prepare the starting compound, biological, with biological property, and with another institute more concerning on regenerative medicine and biotherapy. So just briefly, Montpellier, we talked about this just before. It's not big city. It's medium city in the south of France. Here you have Barcelona. Here there are maybe about 350 kilometers. And it's a city with 300,000 people. Nice city, student city. You have the main place, and it's not so far from the beach. Sergio, do you remember this place? I think.
Yes.
So what's important in Montpellier? We have more than 70,000 students. You know, it's more than 25% of population are students. So if you go to the downtown, you see only students. And north of Montpellier, around the university, only students. So what about research? Research, we have a big center of chemistry. In this building, next summer, we will move, our institute will be there, and IBBM. So in total, we have around 800 researchers about chemistry. Chemistry for medicine, biological property, or materials, all chemists will be located here. In this front, if you see the building seem too small. However, if you look at this top view, it's just behind CNRS Center. So it's not so far from actual place. And this picture was taken maybe 6 months ago. Now it's very ready, the building, and we can move it in 1 month or 2 months, and we have until at the end of 21 of this year. So we will be in this building. Our team will be, I think, this side here. We can see the tennis courses from lab and from our office. So what is, let me talk about hybrid materials. I can give this definition of hybrid materials very simple. It's solid, containing in the same time inorganic part which act as matrix. In general, it's oxide. It can be tin oxide, vanadium oxide, titania, and main part is silica. So silicon oxide. I will explain why silica. And in addition, you have the organic part. The organic part can be linked by covalent bond, and this organic part can give the property of your final materials. And how we can combine both organic and inorganic, thanks to sol-gel process. What's the sol-gel process? Sol-gel process, inorganic polymerization, it's the same. Inorganic polymerization, it's a very old process, discovery by Ebelman, more than 150 years now. And the idea is you started from precursor, organometallic precursor. Here I took the case of tetra-alkoxysilane, but can be tetra-alkoxy tin, tetra-alkoxy titanium, tetra-alkoxy U3-alkoxy aluminum, any type of metal alkoxide. You can activate it by catalyst, and after several reactions of hydrolysis and polymerization, you get first step oligomers and then polymers, and the connection between polymers, you obtain colloidal solution. For this reason, we call sol for solution of colloidal solution, and the connection between these particles, you have gelation immediately. And you get the solid, and you can't go back. It's chemical gel. It's not physical gel. It's not like gelatin at home when you make cake and you pick some gelatin on the top. It's physical gel. Here we have a chemical gel, so you can't go back. And after drying, you can remove the solvent by several types of drying. I don't talk about this. You obtain your oxide. Briefly, the main reaction are hydrolysis. Okay, hydrolysis, it's a reaction between water and alkoxide here to give hydroxide, metal hydroxide, and the cross-linking, the connection between two silicon center can be between two hydroxide or between hydroxide and alkoxide. So we obtain the same results at the end. Silicon, oxygen, silicon, or metal, oxygen, metal bond, and you release alcohol and water and so on. So the advantage of, okay, this in general, we obtain amorphous solid, and it's general ways, as I said before. And the main advantage is this process can take place at low temperature. At low temperature, even at -20, it's work. Okay, it's not necessary to heat. Sometimes we heat a little bit to accelerate, but it's kinetically controlled. It's not thermodynamically controlled. When you have your catalyst, it's possible to make hydrolysis and polymerization. Here, just to have a small cartoon. Okay, we started from tetra-alkoxysilane, and we can get silica. As you know, silica, classical silica, SiO2. The advantage of the silicon, it's in the same column of carbon. They have a similar chemistry. And I mean by this, if you take a silicon carbon bond, it's very stable. Acid treatment, basic treatment, it's stable. You can't cleave this silicon carbon bond. However, if you have a carbon aluminum bond, it's not so stable. Carbon titanium bond, it's not stable because we are not in the same column for this reason only. And if you functionalize, if you remove one epoxy group and you put any type of dye, here just a cartoon by this blue star, and you make the same reaction, at the end you obtain silica, organosilica, I mean. So you have SiO2, but at the end you have organic group on the top, which give this color. So by this way, we can prepare materials as powder, as aerogel. If you make drying under supercritical condition, you obtain hydrogel. It's very light materials and with a nice property. And it's possible to prepare monoliths for separation, for extraction, for any type of application if you need a column. It's possible also to prepare flexible materials if you change the nature of organic group, such some polymers, for instance. You obtain a flexible membrane. Possible to obtain ionogel. Ionogel, it's gel, but containing ionic liquid. I don't talk about this, but it's possible to make doping of your silica by ionic liquid for several property, for maybe conductivity or optical property, and for drug delivery, and so on. So it's also possible to prepare nanoparticles. You stop the polymerization, so you stop at the colloidal solution, so you obtain nanoparticles. And of course, you can make any type of shape if you have your colloidal solution by coating or by casting, by spin or deep coating. So the idea, okay, it's very simple to introduce organic group, but how we can introduce bioorganic unit for biological property. If you look on the literature, a lot of people working on, here we have an example of silica nanoparticles, okay, containing dye for biological application. The author here will immobilize this sugar, mannose, okay? And it's not possible to link it directly. What they perform? First, they make a grafting of amino group. Amino group, you know, amino group, it's very compatible with any type of biological molecules. And okay, PEG, it's just for solubility. And then you have a second step, reaction between this compound and with amino group, okay? At the end, you have a good materials, but the problem, it's 2 steps, sometimes 3 steps. And I will talk about the problem of this amino group. Just next slide. Here you have another example if you want to make a branched polypeptide thin film on the top of any type of substrate. So you have to activate it with amino group. And then reaction between amino acid, activated amino acid by ring opening. You open and you generate amino group here, and the amino group react to another precursor, and so and so, and you can grow. Here you have a linear chain on the surface. Okay, here it seems very clear and easy. So if you took this paper, this review, now it's maybe 7 years ago, they explain very well the problem. Okay, they summarize here to immobilize for any antibody, antimicrobial entity, enzyme, any type or peptide. First step is the activation, okay? Here you have a good activation. If you have some activation like this, it's okay. But the problem, if you can see, here you have the good one. They explain a major time you have multi-layer. So you can't control the immobilization of amino group. So sometimes you have something like this, and sometimes if you take aminopropyl triethoxysilane, you have adsorption of amino group on the surface, and then you don't have on the surface only an H2. You have some alkoxy group, hydroxy group. So it's not very well controlled. Okay, for this reason. So okay, here I summarize. You have to activate, and then you have to immobilize your peptide or biomolecules. And as you know, if you take biomolecules, you have different active site. Your peptide here can be ensured on the surface by this yellow peptide, or maybe by dark one, or sometimes you have another one can become here. So you can't control the approach of your peptide on the surface. Our idea was now it's maybe 7 years ago or 8 years ago exactly. The idea was to design directly the biomolecules containing, look, okay, biomolecules, you have the peptide with spacer and containing the silane. So, okay, the synthesis is not so easy. For this reason, we work with in collaboration. So you can prepare any type of peptide. I talk about peptide, but can be another biomolecules, okay? Can be sugar, can be short fragment of DNA, okay? Any type of biomolecules can be silylated, okay? You will see we can make silylation of collagen-like peptide, a lot of type of molecules. And the idea is to take it directly to use. So you can, if you want to graft something, okay, you take this one and you graft it. If you want to make sol-gel process, it's possible to make sol-gel process and we get your silica peptide. So by this way, we make, okay, we focus, we prepare a lot of nanoparticles with Jeremy. It was Jeremy Sissio, no? You have this paper for him. Multifunctional nanoparticles. I don't talk about this today. And it was possible for us to immobilize it in mesoporous silica for several type of application. And I will talk about this axis today. It's possible to immobilize it on the surface to make antibacterial surface just by tuning the property of peptide, RGD, for instance, antimicrobial, and it's possible to render your surface antibacterial or antimicrobial. And the second part, I divided in 2 parts today, this one, and the second one, I will show you how we can immobilize some biomolecules in hydrogel, okay? In hydrogel here. Here you have hybrid materials, but mainly containing water. You will see some movie how we can prepare it. So briefly, just I show you the synthesis. This work is not done in ICGM, but in IBBM, okay? Because it's a biomolecule synthesis. It's very controlled synthesis by my colleague. It's very easy for them. So we can grow the amino acid one by one. You can manage. It's automatic. You know, we have a robot. You can design your sequence and one by one you can grow on the solid substrate and resin here, resin, and you grow your peptide and then you cleave it. Then silylation here, thanks to this NH2, you can immobilize the silica part or silane part, sorry, and at the end you obtain the peptide silylated. Okay, it's very easy, but you have to work. You have to avoid water. Okay, why? Because this 3-alkoxysilane, it's very sensitive in water. In water, water without catalyst, it's no problem. But you know, we have sometimes some acid and you have some base. So avoid water. It's important to get your silylated precursor pure. So first example here, what we prepare. We prepare this antibacterial peptide with a spacer. Spacer, it's a classical one here. So this peptide was mixed with tetra-alkoxysilane. You know, it's a famous precursor for silica. And you can control the ratio. In general, it's 5% and 90%, 95%. Why? Because it's silica, it's too small, SiO2 at the end. However, your peptide is very, very big. This part don't change. It's only this part move a little bit. So we prepare colloidal solution. Okay, colloidal solution. You put it in your mixer in water and ethanol at pH 2. At pH 2, you have a stable colloidal solution. This colloidal solution can be storage for 3 months or 6 months without any problem. Why? It's stable. If you see here, you have the kinetic of both reaction, hydrolysis and polymerization. The hydrolysis don't take place at 7. Okay, since we are at pH 2, the hydrolysis is very high. However, if you can see the condensation, cross-linking, the reaction between two SiOH to make siloxane bound, it's very low. For this reason, your solution can be stored for several months without any reticulation. Okay, there are no connection. It's very, very low. And the connection take place by evaporation. And now we took glass, okay, classical glass, and you put it by deep coating, okay, you put it in the solution and you withdraw. You can control the thickness. If you remove it very fast, you have the thickness, it's high. If you remove it very slow, the thickness is very thin, okay? It's like honey. If you take a spoon and you put it in the honey and remove, you remove a lot of honey, okay? It's something like this. And after deprotection, you remove it here just by, can be done by thermal treatment or by TFA, trifluoric acid, sorry. And you get your substrate modified with thin film, mainly silica, and sometimes you have on the surface your peptide. The thickness is here around 100 nanometers. And we can quantify the amount of peptide by very simple test. It's very used, this test in biomolecule, because blue Kumasi blue can detect if you have amine or not. And just by reading the intensity of the blue color, you can quantify how much we have peptide on the surface. And by this way, we introduce about 1 peptide per square nanometers. It's enough. Here we have the fluorescence microscopy images. This one, it's for material treated with peptide. Okay, as you can see, there are no Escherichia coli on the surface. Escherichia coli, it's a red color, and you have any Escherichia coli on the surface even after 10 days. Okay. However, in the case of blank, only we make a deep coating only with tetra-alkoxysilane. For this reason, I put this thin layer of silica. Okay, blue one, it's your slide in glasses, and thin film of SiO2 here. And as you can see, a lot of Escherichia coli develop on the surface. It's possible to make same strategy, but you can change the nature of the substrate. Now it's not SiO2, but titanium. Titanium, you know, it's for prothesis. It's very important to make some prothesis antibacterials. And it's possible by same way, colloidal solution and deep coating. Here we have, I summarize it very it's 1 centimeter by 1 centimeter. We prepare it at least 20 substrate, very small substrate. And by thermal or chemical deprotection, you can recover your peptide, and here another type of peptide, unprotected peptide. It's just to show you it's possible to take it protected or unprotected peptide. Both cases, it was possible for us to immobilize it on the surface. And what about, okay, in this case, we prepare several types of substrate in order to characterize our grafting more than first cases. By XPS, it was possible also for us to identify that we have some, here we talk about oxygen. We see clearly different type of oxygen, oxygen of TiO2, of course, oxygen of peptide, CO of carbonyl, oxygen, maybe this one, more important, oxygen between Ti and Si. That means our link, it's efficient on the surface, because, you know, sometimes we suspect a lot of time the TiOSi bond not so stable. And in our case, it was stable because we remove it only by thermal treatment here. Even in the case of chemical treatment, it's not so hard as chemical treatment. So you can keep your peptide on the surface. And here, if you see by carbon, you can see clearly you have a lot of carbon species that the peptide it's on the top of substrate. What about antimicrobial property? The reference, it's a substrate without any coating, and you put the bacteria. As you can see clearly here, the bacteria are very well on the surface. There are a lot of development on the surface. However, in the case of the surface was treated with by deep coating with our colloidal solution, you can see clearly here the bacteria are not very well. All bacteria are die after 2 hours. In this case, the bacteria stay for several days. Another example of grafting. Now we change the nature of the substrate. Okay, first one it's silica, titanium, and now silicon. Silicon for me, it's PDMS. It's nice. We took a catheter from PDMS. You take it directly from pharmacy, and the idea is to immobilize peptide on the surface. I would like to show you briefly how we manage this work. First, we demonstrated that your surface should be activated by plasma. How we found that? We started with just immobilization of amino group on the surface, aminopropyl 3-ethoxysilane, this one. So by hydrolysis, you can immobilize this group directly on the surface. You have silicon, oxygen, silicon bond, okay? And we follow this test by Kumasi blue color. First catheter here, we took it directly, the catheter, plasma, and Kumasi blue without any grafting, just to show you that our catheter don't react with Kumasi blue reactive, okay? There are no adsorption of Kumasi blue on the surface. The second one, it's without plasma. We make a deep coating of the catheter in the solution containing aminopropyl 3-ethoxysilane and follow it by Kumasi blue. It's slightly blue, okay? So we immobilize some amino group, but not enough. In the last one, you can see clearly it's a blue, really, it's after plasma, followed by immobilization of aminopropyl 3-ethoxysilane, and then Kumasi blue test. You can see clearly it's very blue, that you have a lot of amino group on the surface if you activate your surface just before. So for this reason, we demonstrated that all surfaces should be activated by plasma before coating. So, and then how we explain the activation? You have your silicone catheter here. After activation for 4 or 5 minutes, and you break some bond here. You know, PDMS, it's polydimethyl siloxane, no? Polydimethyl siloxane. So you break some bond here, maybe SiO-Si become 2-SiOH. I don't know, we can control that. But however, I will show you that we generate some hydroxy group. And then reaction after coating, you have reaction between SiOH here and SiOH here, you know, the cross-linking. And you can immobilize your peptide on the catheter. Okay, I don't talk about the condition, it's general classical conditions. Yeah, we characterize this catheter before as received. After activation, plasma activation, you can see there are some SiOH group. You have this large band around the 3,000 centimeter minus 1. And what it's interesting, after coating with peptide, you can see clearly the part of NH of peptide is very huge, even the carbonyl. And this skeleton of catheter become minoritor. So that means you have good functionalization on the surface of our catheter. What about biological property? Okay, we compared our grafted catheter in red here and grafted one, okay, as received without any property, antimicrobial property, and we compare it with silver catheter. It's antimicrobial, antibiofilm catheter that you can buy in the pharmacy also. And what we observe, interesting thing, that our catheter here, even after few hours, 12 hours, I think it is 1 day here. Here it's 1 day. So after 1 day, we can talk, there are no biofilm on the surface by comparison to untreated one, and surprisingly, but the commercial one, it's very huge number of iris, staphylococcus. There are a lot of development. And you have to wait at least 15 days for the activation of the silver catheter. We have some explanation, but it's not our problem because it's not what is interesting for us, that for first 15 days, our catheter, it's very, very antimicrobial. How we can explain that here? In general, this catheter, when you, there are some nanoparticles of silver immobilized inside, you have your silicone and you have a film of polymers in which there are immobilization, organic polymers, there are immobilization of particles. And we explain that you need at least several days to destroy this polymer, to the degradation of this polymer for release of silver nanoparticles. Okay, so now, but what I mean here, it's very clearly the immobilization of peptide on the surface give us a very nice property of the materials. Okay, we can prepare antimicrobial membrane. The idea is we took the same peptide, but we mix it on, not with a silica precursor, but with pegylated or silylated PEG. PEG, it's, you know, polyethylene glycol, polyethylene oxide. and we have 2 silane at the end, and we make it hydrolysis and polymerization. And by evaporation, we can prepare this type of membrane. We have a project for smart dressing, so I can't talk about more than this slide, but you can see clearly it's possible to prepare membrane with antibacterial property. I think I have a video, just very fast. You mix all ethanol, water, acidic, and you prepare your colloidal solution. You put it in a Petri dish and in the oven to evaporate. And by evaporation, you can recover your membrane. Okay, let's go to my second part, talking about hybrid hydrogel. It's okay, Sergio, I can continue, no problem?
Yes. Go ahead, no problem.
Okay, thank you. About hybrid hydrogel, let me just explain what is hybrid hydrogel. Hydrogel, it's materials containing at least 95 of water, and you have some organic group. I think you suspect that in our case will be here biomolecule, peptide, and of course the cross-linking should be that will take place by introducing of charge here. It's a polymer, but not simple polymer silylated, and you have the cross-linking here part. So water here, organic group, functional group, the biopolymer, and of course the network. It's not mainly silica, the silica part is very small. Here, okay, mainly it's water, but the ratio between inorganic and organic, it's very low. Okay, and you can manage this to control the flexibility of your final materials. Okay, we apply the same process now to obtain hydrogel. It's how we imagine this. I imagine this like a joke. So like it's possible if you have a lot of pieces. Okay, what's important is to select the good one and to make the good connection to obtain your good final materials. This approach, bottom up, so starting from molecule, you can manage the final property of your materials at the end. If you add one functional group, maybe you have functionality, but it's possible to add 2 functional group, 3 and 4, and so on. Okay, here I put just 2 functional group, just the biopolymers and peptide, but it's not forbidden to add another type of molecule silylated. You can add a dye, you can add another type of biopolymers. Okay, you can prepare big cocktail, and you can hydrolyze and polymerize all together, because the kinetic, it's the same. All the polymerization take place in the same time. So the idea is to prepare hydrogel in one step. Just as I mentioned before, the sol gel process should be activated. Okay, and if you see here, if we want to prepare hydrogel for biological application, we have to take PBS, so water PBS at 7.4 and 7.4, 7.8. And you can see here, at this pH, there are no hydrolysis. If you don't have hydrolysis, so you don't have polymerization. Okay, so for this reason, we have to find another type of catalyst, not acid and not base, but nucleophilic one. I will explain why nucleophilic is very suitable for this type of for this process. And we have to stay in biocompatible conditions. Okay, if we are not in this under this biocompatibility, it's not possible to grow or to make some cells culture on the surface. So we started with F minus. F minus, why F minus? You know, F minus, it's more nucleophilic species. And the link between, it's very suitable to coordinate on the silicon, on the silicon atom. Here, just I summarize why. F minus nucleophilic species can attack very easily this center, tetra-coordinated here, and you get penta-coordinated center. And penta-coordinated center here, it's highly reactive by comparison to tetra-coordinated one. And hexa-coordinated is more reactive than penta-coordinated, and so and so. So first one, activation, and then water can attack here, okay? And then hydrolysis take place, and so at the end. For polymerization, same scheme, attack of F minus and connection now between two hydroxy group. This hydroxy group attack to silicon center, maybe take another one, it's same one, and then you get your siloxane and release of water and F minus and so on. So for the hydrogel, we started first with synthetic polymers. So we took a PEG because it's highly soluble in water and biocompatible, and we silylated by the same strategy, attack of hydroxy here, oxygen on the isocyanate. We took it isocyanatopropyl triethoxysilane under anhydrous conditions. So without any more details, it's enough. It's very easy reaction. You can isolate it very well with high yield. Okay, and I will talk it PEG 2SI. Okay, PEG for PEG and 2SI. It's silylated 2 times. And what's happened if we put it in PBS and sodium fluoride? You know, at 10%, 90% of water, the gelation take place after few hours, and you get your hydrogel. Okay, your hydrogel containing 90% of water, and as I mentioned before, thanks to SiO-Si bond. Okay, this inorganic part, it's here. SiO-Si bond, you have here the polymer and SiO-Si, SiO-Si. Just to show you some cryo-SEM image, just to see that we have a huge porosity. It's important for the delivery, for the connection between, to introduce cells at the end. You know, you need some volume, some space to make cell development inside your hydrogel, not only in the top of your hydrogel. So it's very important to control the porosity. By this image, you can see clearly that we have the hybrid materials here in green, and all this pore can be can receive water and grow factor and so on. So instead to PEG, it was possible for us to prepare this short peptide. Why this peptide? This peptide it's like collagen structure. The idea is to make mime the collagen. To prepare. Why collagen? It's problem because it's animal origin, and you know sometimes you have some infection with and I mean, it's not a problem, but a lot of people for research, we are afraid to use collagen from animal origin to make research in our case, because we are chemists, so we don't have all installation to take care. So for this reason, we synthesize this peptide giving the same property than natural collagen, animal collagen. So it was possible for us to prepare the hydrogel, and it was possible to prepare some membrane. It's just as proof of concept. We started with. And what about adhesion of cell? Here on the left, you have the adhesion here. You can see clearly the adhesion, it's very high. It's very high. It's comparable to commercial collagen here. And our hydrogel, it's here. Okay, so it's quantitative. And what about proliferation of cells? You can see clearly it's similar to natural collagen or commercial collagen or animal collagen. Okay, it's very comparable. And you can see clearly here, the cells are very well on the surface after 24 hours. So here just to have the image on fluorescence microscopy. Here you have blank and our hybrid hydrogel. You can see clearly it's very similar, and sometimes you have some dead cells. Okay, it's not, it's expected because when you synthesize, sometimes you have maybe traces of solvent and so on. So we can, there are some contamination of your starting materials. Okay, another example here. So we go back to the PEG, 9%, and now we mix. Okay, we take monosilylated. The idea is, in order to avoid a huge amount of bicylilated collagen-like peptide, the idea is to put only 1% of collagen-like peptide, but now it's monosilylated, only one silane group, and we mix it with PEG at 9% and 90% of water. We prepared hybrid materials, hydrogel, containing both the biopolymers and the peptide. And we observe that we have more than 90% of adhesion after 4 hours. The mechanical properties can be controlled. If you increase the amount of polymer, you increase here the mechanical property, and of course, if you decrease, you can get the viscosity decrease, of course. Just here, I would like to show you how we select our conditions. You have a percentage of PEG here, sodium fluoride, and gelation time. Why it's important to control the gelation time? It's just for 3D printing. So the idea is we focus on this condition, but because we don't need very fast gelation time and not very low gelation time. The idea it's 1 hour, 2 hours, 3 hours, it's okay. So we selected 10% of biopolymers and 0.3% of sodium fluoride, and you can get your hydrogel like this one after 2 hours. The problem, it was, okay, this cell, there are no cytotoxicity after 24 hours, even after 48 hours, but the problem, after 3 days, all your cells are dead on the surfaces. We explain that by the F-. F- it's cytotoxic for cell at this concentration. Okay, so the idea is to find a way to increase, to decrease, sorry, this concentration of F-. The idea is to work about 0.1%. At this concentration, we are biocompatible. The idea is to add something to activate, because at 0.1% of sodium fluoride, you can see clear here, where is, sorry, here, 0.1% here, concentration, no toxic, but the gelation time is very slow. As I mentioned before, at 0.3, okay, it's fast gelation, but it's toxic. And what we found is that if you mix F- and glycine, it's amino acid, it's possible to manage your gelation time, and the toxicity, cytotoxicity is very, very low. Just, I would like to explain you why we need to control the gelation time. As you suspect, the idea at the end is to possible to print this hydrogel to make a shape for implantation, for cartilage, for example. You can make injection, but sometimes you open and you make some implantation. You need some form of this hydrogel. So with 3 milligram, it's highly toxic. 0.1, it's not toxic, but it's very slow. But the idea is to make something to find the catalyst and co-catalysis to be here in this window. Even here, it's not problem, but not so fast. It's okay for us. It's very, very fast, but it's not possible by adding only glycine. You have to increase the amount of sodium fluoride. So we have to be here, stay here. So we selected several type of compound, diol, amine, ethiol, amino acid, and we don't find anyone better than sodium fluoride alone. However, if we add both F- and the glycine, it's possible to obtain co-catalysis system at 37 degrees with 10% of silylated PEG. So I summarize here: sodium fluoride alone, 3 milligrams, very fast but toxic, very low but not toxic. So, and we find several possibility to manage the winding, the printing window here or here or here. I select only two by adding 0.1 milligrams of F- and glycine at 0.7 molar. Okay, it's possible to get your gel after 14 hours. So, okay, you prepare it. For example, today, now at 7 o'clock afternoon, and you come next day, you can print it. Okay, the idea it's to find the printing window. And if you decrease the amount of amino acid, so the concentration is 0.1 molar, okay, you decrease the gelation time. So you can prepare it and you go at home, you go back the next day, you prepare your syringe and you can print it. I don't know if I can talk about NMR. I think we don't have time, but how we can follow the gelation time, the hydrolysis by NMR. By NMR, just I would like to explain one point. You can follow the diminution of this signal, for instance, proton 2 here. Okay, we can see clearly after several hours you decrease, and in the same times you release some alcohol, ethanol. So the formation of this methyl group here in blue, and you can see the increasing of this one. So this one is with 0.1 milligrams. However, if you add glycine, 10 milligram per milliliter, we have the same shape, exactly same, but it's moved, it's shifted to short time. Instead of for instance, here, the maximum of hydrolysis, it's about 40, 45 hours. Here, look, it's between 10 and 12. So you decrease your gelation time very easily, and this can be controlled very well by NMR. Okay, just I would like to explain the effect. Okay, minor effect if you protect your glycine amino side or acid side. If you take a mixture of methylamine or acetic acid, there are no effects. However, when you add this one, a huge effect. How we explain that? After coordination of F-, the amino acid become here as chelating group to increase the reactivity of the silicon center. And then now water can attack and the hydrolysis and polymerization take place. Okay, it's not necessary to explain more, but all this was controlled by silicon NMR. Okay, really, it's my last example now. So we move it to natural polymer. It's not synthetic polymer. So we took hydroxypropyl methyl cellulose. Okay, the idea is to silylated. Okay, some group in France are silylated before us, but the problem after their silylation, it was necessary to apply alkaline treatment to isolate their polymer. And it's very big problem to make cell culture because you have to neutralize, and it's not so easy. Our idea is to silylate it directly and to use it as isolated, without any acid or base treatment. So we took HPMC reaction with isocyanatopropyl trialkoxysilane, and it was possible for us to control the silylation rate just by changing the ratio between ICP-TS and HPMC here. Why? And by, as before, by NMR, you can calculate, you can estimate the silylation rate, okay? Just by integration of this proton and this one, C or D, whatever, red one or blue one. And you make the ratio, you can obtain your silylation rate. And we isolated without any problem with a quantitative yield as powder, and it's stable for several weeks at room temperature without any specific conditions. So by silicon NMR, we showed that we have intact our silane group. It's only T0. Maybe it's very strange for you. T0, there are no connection with another one. If you have a T1 and T2 and T3, that your cross-linking start. The idea is to demonstrate that in our synthesis, we have silylated precursor without any destroying of this part. Okay, and we generalize this synthesis to another type of biopolymer, dextrine, chitosan, pectin, hyaluronic acid, and so on. So just I would like to show you now last results. So we took it and we put it in PBS with a mixture of F- and glycine. We prepare the hydrogel. You can see it's very transparent hydrogel. Stable hydrogel with mechanical property can be controlled by changing the mass of your biopolymer or the silylation rate or the concentration from 1 to 12. It's possible to obtain that. The best one, if we want to summarize between gelation time, mechanical property, and the printability, it's to make 3D printing, it was the polymer with 30,000 of mass, and at 6%, and silylation rate 16. So, okay, by this way, it's possible to control. If you need something more flexible, okay, you can decrease the silylation rate, you can decrease the concentration, or if you want to keep both here, you can decrease the mass. Okay, we have several solutions. Okay, cryo-SEM as before, you can see clearly we have a good porosity and so high accessibility at the end. And I would like to show you, maybe I don't know if it will work, how we can print it, okay, before gelation, okay? Just you have hydrolysis, and just before solidification, in general, it's between 2 or 8 hours, we can print it. Sorry for the noise. But look, you can control. Okay, we have, in general, we have between 40 minutes and 1 hour 30 to make printing. If you wait more than this time, it's not possible to print it because the viscosity decrease, and it's not possible to make. No, you know, we can make several layers one by one without any problem. And what we have done recently, you can put the cell inside. You print your hydrogel containing cells, okay, without any problem. Maybe I will stop because it's the same. Okay, we can print it directly, and you can recover it. Here without cell, of course, but you can recover your hydrogel. It's you can cut it, and you can put it in another petri, and you make cell culture on the surface, and you can control the size. In general, it's 2 by 2 centimeters. You can change the form. And what about cell viability? It's okay. Both cases, after 1 day or 7 days, it's very similar. It's about 60 and 65. It's not so high. I know that it's not so high. We suspect the cytotoxicity by the traces of organic solvent remain in the starting precursor. Okay, and there are no difference between pipetting of cells or introducing of cells by 3D printing. 3D printing, it's B&D, and by pipetting here you print and then you add your cells. Here you print your hydrogel containing already cells. So as you can see, there are no difference. Okay, after 7 days, the cytotoxicity, it's around 60%. Sorry, I don't, yeah, oh, okay, it's the last one, no? I can continue, sorry, yeah?
Of course, if you can, go ahead.
Just last one, last one.
Okay.
It's just to announce next step. As proof of concept, what we have made, we prepared, okay, 1% of silylated fluorescein just to be observed under fluorescence microscopy, and we added HPMC silylated or PEG silylated, and we demonstrated that it's possible to make 3D printing. And you can see clearly, even if you are in water, the dye fluorescein remain inside your materials. The idea is for the next step, if it's this part, it's work. And now what we are doing, it's my last slide. We are going to, okay, to prepare the same thing, biohydrogel, containing, okay, biopolymer, it's not problem. We have a lot of possibility. Silylated peptide or bioactive with growth factor and with cells. All together, we would like to prepare, we are now to prepare to find one way to prepare hydrogel containing cells in one step. And the idea is to make 3D printing as before, maybe for implantation or for directly injection. So now we have 3 students working on this area, and we hope to obtain something new recently. So I would like to thank all people participate to this work. This work started in 2012, 2013 by 2 postdocs. We have a collaboration with Axelair and Montpellier University. We started with 2 postdocs between 2013 and 2015. And thanks to these 2 postdocs, we get several fellowship for PhD. Cécile Echalier working on the PEG hydrogel, and Titouan on HPMC, and Laurine, PhD student, now she's working in Paris. Titouan, I would like to explain for you, after his PhD, he took 1 year to travel around the world. And 3 months ago, he was in Mexico visiting, for visiting, and he want to go back next year to start a job. He decided to take 1 year stopping. So I would like to thank, of course, my colleague Gilles Subra and Professor Jean Martinez from IBBM for the biological part. And of course, for all partners, we have a lot of partners, local partners, CNRS, university, and ANR, it's from ministry. And thank you very much for your kind attention. And thank you again, Sergio, for your invitation.
Au contraire.